Okay. Let me begin by thanking all the organizers for this meeting, and in particular, Claude and Michaela, who had a lot of work with this. I'm very happy to be here at this occasion. Lumini is always a wonderful place. Oops, what happened here? Yeah. Before I start my talk, this conference is dedicated to two people, Michaela and Hassan. And since I have your attention and a projector, I wanted to show you some pictures, the other life of Hassan that you might not know. So what's going on here is that both Hassan Zadok and Michaela have made numerous contributions to numerical linear algebra. Also, there's approximation theory involved. What comes to mind, extrapolation methods, ill-post problems, breakdown of the Lanzos method. I mean, these are papers of Michaela and some of them with Hassan, which I've very much enjoyed reading. And so, I mean, in English, or at least in the US, one could say, oh yeah, Michaela and Hassan kick ass. They know what they're doing, but what some of you might not know is that Hassan really kicks ass. I mean, literally. Michaela is way too sophisticated. But let me see here. Yeah, so here's Hassan, and so he does Taekwondo. And this was some special issue. I mean, you read better French than me, but this was a special issue that came out when he became Secretary General for the French Taekwondo Federation. And I don't think this is made for mathematicians, right? Because there is a Bond equation, but it's never defined. But there he is. And here's another picture. So I mean, you better think twice before you write a negative referee report. He may be at your doorstep. So anyway, so let's get started. So we'll talk about some joint work with people that have an association to Como, all of them. And some of you may know these my collaborators. Davide Bianchi, he has tenure in China, in Guangzhou. I mean, this is close to Guangzhou. And he just got tenure fairly recently. But he's really Italian, as the name would tell you. So what we are talking about is Arnoldi-Tikhonov. And so the starting point is that people like me and many others, when we solve ill-post problems, we discretize them, even though ill-post problems naturally live in Hilbert space. But we discretize them with computer solution of the discretized problem, and are happy we never look back. And the question is, well, what's the impact for the continuous problem? And often this is not really addressed. In a joint paper with Ronnie Ramlau, we looked at that. It works, but I at least was not super happy with the accuracy we got. So, I mean, so the idea here is that we start with a continuous problem. Of course, we discretize it, and this gives us a large matrix. And in order to solve this linear system of equation, which comes from a linear ill-post problem, we use the Arnoldi method to reduce a problem to a small size. And we try to keep track of all the errors that we do. And to improve the accuracy, we use not only Tikhonov regularization, but iterative Tikhonov regularization. And the fact that the iterative Tikhonov regularization actually works better than just standard Tikhonov regularization is known. I mean, here, and these are not the only people who worked on this, but I found some people who are here in the audience, right? Worked on this. And so the problem with standard Tikhonov is that when you start to solve these ill-posed problems, you have data, and the data is contaminated by error. I mean, think of AX equal B. B is the right-hand side, it's contaminated by data. And the question is, now when we use Tikhonov regularization, because A is maybe numerically singular, the question is, how quickly does the computed solution converge to the solution of the error-free problem when the noise in the data goes to zero? And it's not that quickly. I mean, it does converge, but not so quickly. And it converges faster if we use iterative Tikhonov. So that is our interest in this. So here's the starting point. So we have an operator equation, Tx equal y. T is this operator from one Hilbert space to another one. X dagger is the solution we want. So y here is, we think of this as an error-free data. If there is no such solution because T happens to be singular, well, then we think of the least square solution of minimal norm, right? So that's where the Moore-Penrose inverse enters. And what makes these problems special is that T has an unbounded inverse. So T as an operator is bounded, but the inverse is unbounded, which means if we have a small error in y, then the error in the solution could actually be arbitrarily large. So we will assume the presence of two errors. One is in T is replaced by TH, and that's a discretization error. And then we have the error in the data. So instead of having y, we have y delta, and there is the error we assume that we know a bound for the error. I mean, this is more a technical assumption. If you actually want to solve these problems, one can get around that assumption. So what do we need? Well, we discretize the problem. So we need a couple of subspaces. They are called x1 through xn. They're all subspaces. We need orthogonal projectors from x to the subspace xn. Yn is the image of x under T, and Q is a projector from the range space to the projected space Yn, and then we need an inclusion operator which goes from small space back to the big one. And here we apply these operators and we get the first equation up here, right? And this piece, Qn T In, is we can think of that as a matrix, an n by n matrix, right? And so instead of solving Tn(xn) equal Yn, which we have there, we solve this one with the perturbed right-hand side. And we are interested now in, well, xn is the error, is the solution of the error-free problem. And we are interested in, well, what xn dagger is the solution we get in the error well, this one is the solution we get of the error-free problem here of Tn x equal Yn. And we assume that there is a function here, Fn, such that which goes to zero when we discretize more and more. And the way to handle these things here is to say, well, we now go back to linear algebra, right? After all, this is a linear algebra meeting. So we have a basis. We say S1 through Sn is a basis in this n-dimensional space. Yeah. Yeah, we don't want an accident here. We want, so we have so S1 through Sn is a basis in the low-dimensional Hilbert space, and then we switch to linear algebra, and so we look at the coefficient xj superscript n. And we will basically assume that the discretization is done so that the 2 norm of the coefficient is proportional to the x norm in the Hilbert space. And I mean, this can be done with a variety of bases. If you use hat function or finite elements, orthogonal basis. I mean, if you use finite elements, you shouldn't have a too weird discretization, but then this all works, right? And so here we have Tikhonov regularization. So the alpha is a regularization parameter, and I will get to how we want to determine it, but the, say, normal equation for this minimization problem gives us the solution here, right? And we are thinking of the situation when Tn is fairly large. So there are papers which have been inspiration here. There's one paper by Nutter from the 70s, and he discusses, well, he says, we discretize the original problem, and he observes that if you take an ill-posed problem and you discretize it, typically it's not so ill-posed anymore, so then we can solve it. And so one way to show convergence is to not discretize too much. The problem numerically is that the discretization has to depend on the amount of noise, amount of error. And we don't know that. So, I mean, one way to implement the Nutter approach is to say, well, we discretize on different measures, and then we choose one which is appropriate. But it's easier to discretize on a fine mesh, n, where n is kind of the mesh size, and then use Tikhonov regularization to take care of the ill conditioning. And part of this work is also inspired by work by Neubauer from the 80s, who did this in different steps, but he never used Kirchhoff methods, right? And so I don't think that this slide requires a lot of attention here. It's just we take Tn and we reduce it to a small matrix, which will be called Hn, and the elements in Hn are these here, elements H, right? So here we have the Arnoldi decomposition. The matrix cap V consists of the vectors V, which are generated by the Arnoldi's process, and they span this Krylov subspace K. And so now what we're going to do with this, well, here's H, that was a Hessenberg matrix. When we put the non-zero element Hij in the matrix, we get this Hessenberg matrix in the Arnoldi decomposition. And here it is again on the top line, the Arnoldi decomposition. And then how we proceed is, well, we take this top line and we multiply it from the right by VL, well, transpose, right? And then we just say, well, what about if VL transpose is the identity, then we are happy, but otherwise we just ignore that. And that defines my operator TL here. So this is a big matrix, and it is of rank at most L. And we have to require that we have a bound here. And how good is this bound? Well, that's sometimes not always so easy to determine, but we do know when L increases, then the bound here, this difference goes to 0, right? Because when L is n, then we have this identity here, right? So in the Arnoldi-Tikhonov, we use this matrix TL, superscript Tn superscript L. So this is a huge matrix, which we, of course, don't want to work with. So then we use these matrices. We assume that y is of this form, and we multiply through by VL, and we use that VL has also normal columns, and so we get this reduced problem with a small matrix. And we are happy. And then if we use iterated Arnoldi-Tikhonov regularization, well, the way it goes is that will be our regularization problem. So we start with I equal 1, to then this part, the last element here is 0, and this is a problem we already have, that's standard Tikhonov. And then we apply Tikhonov again, doing what we compute is a correction of the solution we have in the previous step. And we do this a couple of times. And we can, if we so wish, write the solution in this form, or even better, we write it down here in terms of the small matrices H. And so this is what it's a small matrices H which we use in computations, of course. For the convergence, we need the SVD of this little matrix H. And then one has to show, then the question is, how do we determine, how do we determine the regularization parameter, the alpha? And there is an equation here. And E is a constant. HL was the error when we use Arnoldi. And delta was the error, a bound for the error on the right-hand side in our data. And this is just an equation for alpha. And we have to require that somehow these errors are small enough compared with the error in the data. So that's what this equation tells us. And then the equation here for alpha has a unique solution, and that's the solution we use. That's the alpha we use when we do iterated Tikhonov. And what one can show is that, well, one way to look at it is to say, well, the alpha we chose is maybe a little bit too large, but what we can show is that if we choose it larger, we get a worse solution. And proposition. And the second one, here we look at the rates of convergence. So in this equation, we are still in finite dimension space. There this is what happens when we let delta go, when we increase I. So I are the number of iterations in iterated Tikhonov. And when I is 1, this part is just 2 over 3. So when delta, the error in the data, goes to 0, the error in the computed solution goes to 0 as delta to the 2 over 3. And while if we increase I, then 2i over 2i plus 1 converges to 1. So we improve our rate of convergence. And the bottom is when we go back to Hilbert space. And then we get another error, Fn, which was related to our discretization. But that's it. So let's see how this works. Oh, I'm fast. We use just a simple test problem to give you an idea what's going on. So what's going on here is when we I is the number of in iteration, in iterated Tikhonov. And what A is a matrix. I mean, we discretize, we get a matrix which is 1,000 by 1,000. The error on the right-hand side is 1%. And then we look at the number of in iterations and increase that. And what we see is that the error in the computed solution, the relative error, decreases. And see, if we do 200 iterations, we decrease the error by a factor 10. And which is somewhat substantial. And you want to say, well, 200 iterations is a lot, but the L is 10, so we solve a 10 by 10 problem 200 times. So this is not too much of an issue. In the bottom part here, you choose L equal to 20, so now we solve a 20 by 20 problem, and it's pretty much the same story. If we do Tikhonov one step, this is the error in my computed solution, and if I do Tikhonov 200 steps, well, my error is almost a factor 10 smaller. Yeah, I have another silly example. But now we do image restoration. Of course, not really. This is just a toy example, but it's easy to implement. So therefore, we did this. So my matrix is n square by n square block Toeplitz matrix with Toeplitz blocks. And we have a matrix which is of size 900 by 900, and then we look at the number of inner iterations. And what we see here again is, well, this is where we start with standard Tikhonov, that's my relative error. And if I do 300 iterations, I reduce the relative error by a factor 10. And yeah, I mean, it's a fast method, and therefore I'm also almost done. So here's the exact image, and here is the restored image. Yeah, this is maybe not a state-of-the-art method to remove all the edges, but the point here is to show that iterative Tikhonov works very well. And while the theory, this is not so surprising in a way. I mean, theory has told us before that, yeah, iterative Tikhonov should give us a small error. What was the surprise was that the error is this much smaller, and that you actually have to do quite a few more inner iterations. But so this is, we will see how things work out. This is just proof of concept examples. Thank you.